Welcome, everybody. And we have now our keynote speaker, Anandkumar, and I am very, very pleased to be able to introduce her to this community. She is Brem Professor of Computing and Mathematical Sciences at Caltech, where I did my PhD, so my alma mater. And she's also Director of Machine Learning at NVIDIA. She was the youngest named chair professor at Caltech and has received many, many awards in a short time span. But beyond this, also Anima is a relentlessly outspoken and influential leader and woman of the times, and having spearheaded many campaigns in the community of machine learning for improving our community. Her campaign for renaming NeurIPS, the conference, one of the flagship conferences in machine learning, got her the recognition of the 2018 Good Tech Awards of the New York Times. But in terms of research, of course, she's a pioneer of tensor methods and a force to be reckoned with in the machine learning community. So with that, I would like to pass it on to her. And she's going to present, and I will hide my video at that point.
Thank you, Lorena. And that was just such a great way to connect. Yeah, I hope you had a great time at Caltech. I always continuously strive to have more women and underrepresented communities be at Caltech and help us further enhance our research and other aspects of community life there. So, and I'm really pleased to be here today. And Project Jupyter has been close to my heart. I've, been using notebooks all through my research career, and now my team. This is the way we prototype. This is the way we then share the knowledge with the world. Open sourcing is a great aspect of the current culture in machine learning. Democratization of AI is built on the foundation of open source, and Project Jupyter has been great at enabling all this and beyond, right? So first is in the aspect of notebooks and prototyping, but also having reproducibility and transparency in AI has been so crucial. And over the last few years, there has been such an immense push towards enforcing this in our conferences. For instance, NeurIPS this year has a reproducibility challenge. I think all camera-ready papers have to come with code. Now Archive added a tab like where you can have code along with the papers. So I think this aspect that machine learning and AI is no longer in the theoretical realm, right? Once it starts getting into the practical realm, source code is such an important aspect. Pre-trained models and the model zoo are important. Testing tools are important. Profiling and monitoring tools are important. So this whole ecosystem of the AI stack and infrastructure becomes such a critical part of enabling this in practice. And NVIDIA has indeed been at the forefront of building this ecosystem, building platforms, building frameworks, in addition to the GPUs, to enable this AI revolution. So let me start with that, and I'll give you an overview of some of the latest frameworks and platforms we're building, along with the algorithmic research that goes with it, right? Because my background, as Lorena was saying, involves looking at tensor methods and other methods, first from the theoretical lens, understanding when these can do well and when they don't. And now, seeing them in practice has been a dream come true. And so seeing also how we can enable new algorithmic research and have that be synergistic with development of these frameworks and platforms. So with that, I'll start sharing my slides now.
They look great.
Awesome. And I imagine that people can ask questions in the chat. And Lorena, if there is some immediate clarification, feel free to interrupt me, something that doesn't need to wait until the end. But if it's
okay, I will be looking at the Q&A at the chat here in WebEx and also in the forum, and I will make sure to transmit any questions to you.
Got it. Thanks so much. So with this, I'd like to start with the exciting deep learning revolution we are seeing over the last decade. And that has been possible due to what I call the trinity of AI. So AI is not just the algorithms, it's not just deep learning, but it is built on the foundation of having large data sets such as the ImageNet and large-scale compute from GPUs. So this confluence has led to the ability for us to have large-scale neural networks that are being deployed in a variety of applications. Indeed, we've seen exciting results all the way from AlphaGo beating the human champion to the NVIDIA GAN passing the Turing test and generating such photorealistic high-resolution images of faces of people that never existed, right, or that do not exist. So having this ability is much further than what any of us had expected when we started working on this a decade ago. But even with this, there is a lot that is still left to be done. There's been so much excitement around autonomous vehicles and autonomous systems, but we haven't seen it one yet be deployed at large scale in the streets. And the reason is safety criticality is so difficult for the current systems to perform. There's a long tail, and looking at all possible scenarios in the real world is hard. And any mistake could lead to life and death situations. So that aspect makes it very challenging. Language understanding is another one where we've seen lots of very impressive developments with the availability of large-scale language models. But still, I mean, given the pandemic that we are facing, and when there was an attempt to remove the human content checkers with AI, it wasn't still ready, right? And it isn't still ready because understanding all possible uses of language is still beyond the realm of current models. And when it comes to robotics, we are still far from having adaptive and intelligent beings, like even like our pet dogs. They may fumble, but they attempt to learn new skills. They interact with us. They attempt to understand us. And most of the robotics, on the other hand, is pre-programmed and cannot adapt with data. And so robot learning is another cutting edge field. And I'll show you some platforms and frameworks where we are developing new algorithms. So the question is broadly, given where AI is today, how do we push it to the next realm? How do we make it adaptive? How do we make it learn with just few examples? How do we make it robust to noise like humans have the ability to do that? So these are questions we want to ask to lead it beyond the current realm of narrow AI to generalizable AI. And in this case, I want to break down any AI algorithm into first two parts, right? So one aspect is the learning, the other is decision making. Because you can learn on some data, but you also then want to decide how to use that model. And so you can think of decision making as having aspects of what tasks should you design this for? How should you design the objectives? How should you design the deployment of these models, as well as what action should you take if this is an interactive environment, like say a robot interacting with the environment around it. But within learning, there is further division. We mostly think of learning as using data, but there are also priors. There's priors of the world around us. And currently, deep learning models don't use a lot of those priors. And so it's an open question of how to build those better priors. And if you think about current deep learning methods, most of that requires massive label data sets that require expensive human labeling. They are having just weak priors. For instance, for all images, we use convolution, right? But we don't make it domain specific. For instance, in autonomous driving, it's very important not to make mistakes on signs such as the stop sign. And experiments have shown that even if you add simple blocks here like this, you can fool the system into confusing what's in the sign. So this brittleness is now a real problem for many of these AI models. And the question is, can we design better and robust priors? And much of my recent work has focused on this, whether it's getting inspiration from neuroscience and adding feedback into feed-forward neural networks, or to utilize existing controllers in robotics, and or to use domain knowledge from quantum chemistry to have good, robust features that are transferable to larger molecules. I won't talk about all of that today here, but if you go to my website, you can see great examples of where adding the right domain-specific priors will make it much more robust and transferable compared to the baseline models. And lastly, we have to be mindful of the tasks on which these models are being trained. We researchers are attuned to this culture of leaderboard chasing, where we all accept a benchmark and we try our best to beat the current methods on it, right? But that can lead to dangerous consequences. For instance, it's now well known that face recognition models that are available through some of the companies are extremely biased against darker skin tones, and especially Black women and men. So in this case, if they're being used in law enforcement and other sensitive applications, you can imagine all that bias amplification happening. It could even lead to life and death situations. So it's important when you're thinking of doing your research or putting it in deployment, what kind of benchmarks should we design for training and testing? And can we go beyond the current culture of just accuracy, or accuracy being the metric? So these are all aspects to think about. And where I see the next frontiers in AI involves moving from supervised learning to unsupervised learning. So a lot of research in my groups, both at NVIDIA and Caltech, is focused on how to do practical unsupervised learning at scale and how to derive inspiration from how humans do disentanglement learning, how humans can disentangle different variations, how they can learn new concepts. We have some exciting new works in this area, but today I won't be talking about that. I'll focus on the priors today and ask how to design better, robust priors, whether it's incorporating domain knowledge or adding structural priors. And we'll see how tensor methods can give a great set of priors for the ability to train good models. On the task side, we've been looking at adaptive tasks, which are in multiple domains, which are dynamic, but these are, again, aspects that I won't be covering today. But I wanted to give you an overall view of where we are headed in the next decades when it comes to development of AI. We want to focus more on unsupervised learning, development of better and robust priors, and design of more adaptive tasks. And indeed, a lot of inspiration comes from studying as humans, and especially infants. How do they do this amazing learning? They're doing it predominantly as unsupervised learning. So all those are aspects that should inspire us to do better and more robust AI. So now I want to get into the frameworks, and in particular show how we've been working on tensor methods over the last decade, and what are the frameworks that enable it to scale efficiently and develop new code and new methods without even knowing all the underlying details of these methods. And that's where Tensorly is an open source framework where we've been extensively developing for tensor methods. And that, as I said, will enable good structural priors. And so the idea is, tensors and graphs and laws of nature and other forms of priors are really important in many applications. So what is a tensor? It's extension of matrix to higher dimensions. Thanks to this cartoon where dogs are always a great way to describe abstract math and make it more friendly. But the idea is really, how do I now expand beyond just rows and columns to more? But it's not just a multi-dimensional array, right? So just as we multiply matrices, just as we have low-rank matrices, we can ask the same question of how do I interact different tensors together? How do I manipulate them? How do I express low-rank tensor aspects? So putting all this together means we can extend matrix algebra to tensor algebra. And there's been extensive work done in this in the past century, but bringing that to the practical realm and bringing that to machine learning has been an incredible journey for me and my collaborators. And indeed, so much of what we see in machine learning involves tensors, right? In fact, if you go to TensorFlow or PyTorch or any of these, right, that's a data tensor. I mean, the name tensor is in fact in TensorFlow and tensor cores in NVIDIA GPUs. So, but the understanding of tensors there is in terms of having multiple dimensions. The question is, can we think beyond and ask how to retain information in these multiple dimensions efficiently? What kind of low-rank representations can we design? And why should we have a neural network with just matrix layers when the input is a tensor, right? So can we go beyond and design tensor computations in our neural network layers as well? So these are aspects we've been building in Tensorly. So Tensorly is an open source framework that was first started by Jean Koseifi and now enjoys an extensive open source community. And the idea is making this accessible to a wide community, not just in machine learning, also in quantum chemistry and areas that require tensor computations. And the idea is having many different backends, right? So for instance, somebody in the quantum field may prefer NumPy, whereas a machine learning researcher will prefer PyTorch, or even the latest one is JAX. And QPy it will enable GPU acceleration for Python. So all these different backends you can easily fix. And the idea is there is a stack of operations from simple manipulation on tensors all the way up to having ready-made neural network layers that are tensorized, so you can start using them in various applications. And there is a whole variety of notebooks on GitHub here. I won't be running them here due to lack of time. I'll just show some code snippets, but please go ahead and access them and play with them. And indeed, you can install this. This is open source. So all these instructions are now available, and we've just released a new version that's out now. So take a look at this. And so the building block for all this is to extend matrix product to now more dimensions. Right. So the question is, I think showing this pictorially hopefully clarifies what we are saying here. So just as you can multiply a matrix with a vector and think of that as linear combination of columns, similarly, you can now multiply a tensor along different dimensions and similarly do these combinations. Right. So the idea is in a matrix, you can only multiply on two sides, whereas in the tensor, you can now multiply in all those different dimensions. And so in Tensorly, as you can see, this is just one line of code, right? So you can directly express these contraction operations. So with this building block, then we can design methods that express low-rank structures in tensors. So the most popular version is known as CP decomposition. So unlike matrices where there's only one notion of rank, in tensors, that is in dimensions 3 and beyond, there's more than one notion. And CP decomposition is one of the popular notions. And in Tensorly, what you can do is you can just look at recovering the CP tensor, right? So given any tensor, just say, give me the CP decomposition. And So in this way, it's just simple operations to do these, recover these low rank decompositions. And you can also keep the tensor in a low rank form. So the idea is, even in case of a matrix, if it's a low rank matrix, there's only a row and column. But if you multiply that, that could become a huge matrix, right? And that's really wasteful to directly operate on this large matrix. Similarly, in the tensor, you want to keep the low rank form as it is throughout the chain of manipulations. If you expand it, you will many times run out of memory. And Tensorly enables this with end-to-end operations, and it'll also speed up because you're now directly operating on the low rank forms. And so you can keep this as a CP tensor throughout all the operations. So the question is, how can we use these forms of tensors in different networks? So the first work we went about doing was my first collaboration with Jean Kosefi and here others. So, and the question was how we can change matrix operations in neural networks to tensor operations. And the first one we went about doing was Tucker decomposition. So the Tucker is another form of low-rank decomposition. And the idea, as you can see here, is there is a core tensor, right, that's of smaller size than the original one. And then there are factor matrices that then expand it to the original dimensions. And again, in Tensorly, that is just one operation to get this Tucker decomposition. And so how we went about using this Tucker form was to compress fully connected layers. And so in the last layer, we can now use tensor regression, where we express the weights in a Tucker form. So now it's low rank, it'll have much lower number of parameters than the original one. And by doing this, in fact, we got space savings as high as 65% in standard ImageNet benchmarks and architectures, and without any loss of performance. So this shows that having tensors can compress your layers by huge amounts. It can speed up operations. So there is a much richer set of architectures beyond just matrix operations to get these neural network architectures. And Jean also applied this to MRI data. You can do regression in all forms of data, and with this is 3D ResNets because this is 3D data, and so there's even more potential for compression as well as robustness. So another interesting feature was by using tensor representations, we have much better inbuilt robustness compared to the baselines. And you can also use this for domain adaptation. If you're now having multiple domains, an efficient way to transfer information is through having a core tensor that is common to different domains. And this should be much better than simple vector or other representations that people typically do in practice. And then Jean also looked into other forms of incorporating tensors into different layers. And in this case, it was convolutional layers, right? So earlier we did fully connected layers, but then there's a lot of potential to compress and speed up in the convolutional layers as well. And especially with 3D convolution. So if you're doing full 3D convolution, that's too expensive. And so can you express this as a CP decomposition? So you can think of this as sum of separable convolutions, right? So this way, we hope that we can, by having enough such factors, you can still correctly capture the relevant features in the images and videos to get good performance. And they did it for emotion estimation. And indeed, there is a whole range of emotional states. And, this was the data they carefully collected. And what they were able to show is that the model has very good performance with a tiny number of parameters compared to the other state-of-the-art models. So you're getting like, having just 1/5 of the parameters and having better performance. And I think that's what is surprising in all these models is that, bigger is not better. You can get better performance with a smaller model, which is not seen at all in any other setting in deep learning, which is what makes tensors so intriguing. And that's what we found also in this other work, where the goal was to incorporate better temporal information. So right now, if you're doing LSTM models, there is only short-term memory. So if you want to predict way into the future, that fails. On the other hand, transformers are still too expensive to do large-scale videos end-to-end to capture all temporal correlations. And that's where we designed tensor trains as an intermediate point between transformers and LSTMs, because now you can factorize the temporal hidden states over a window and capture the correlations effectively. So the idea of a tensor train is you have now a train of values. I mean, there could be many of these blocks here in the middle, and you go from the beginning to the end. And that's what we built into convolutional LSTMs, where the tensor train now takes a window of hidden states and then looks at their higher order correlation and expresses them as a tensor train, which is low rank and hence compact. And when you train this end-to-end, what we see is that our model has extremely small number of parameters compared to state of the art. So you can see really impressive compression here, but still doing better, right? Doing better, whether it's some terms of perceptual scores or SSIM and other standard scores for video prediction. And we also saw this, if you want to detect the activity early, as you can see, the convolutional LSTM with TensorTrain detected this much earlier compared to the other models. So it's not just a compact model, it's able to detect activity early. And that's so important in so many settings, whether it's disruption in chemical plants and other processes, some suspicious activity. So all these are aspects that require early detection. And that's where these models can be effective. So given now we did this work at NVIDIA, of course, the question is, how can we make this model efficient and to make use of the infrastructure and the tools we have to get good GPU utilization? And that required using automatic mixed precision. So in addition to having these compact models to begin with, we can further quantize and get even better performance and better memory savings. Having GPU optimization of fusing different kernels, and this LSTM activation checkpointing, which led to huge savings in memory. So, and then ultimately also having multi-node training and model parallelism and using multiple streams. And so the idea is, we can get much faster training, much better utilization of GPUs, better GPU memory usage. So all these are aspects we can combine as we develop new algorithms such as this one. And also at NVIDIA, that's the aspect, right? How do we make efficient use of GPUs and design good, effective primitives? And to do that, we are moving up the chain, so to say. Meaning if we can block and look at primitives that compute more complex operations, but doing that effectively and in a parallel way, then we can get much better savings. And that's where tensors are also really effective in better utilization of hardware. So once we have those primitives, tensor models now will be much faster than the ones with matrix operations, because they're further having more effective blocking and parallelization. And the NVIDIA CUTENSOR is a library that is using a high performance set of tensor primitives, such as tensor contraction. And we're now building that into Tensorly, so you can access this high performance primitives without worrying about low level details and directly program in Python. And so you can get both good performance and ease of use by having this ecosystem of frameworks come together. And indeed, now with the Ampere tensor cores, there's even further parallelization and thinking about blocks of operations using tensors. So that's where CUDA library like CUTENSOR can be very effective. So to summarize this thread, what I showed was having tensors as a way to provide higher order primitives for deep learning is very effective because we no longer need to restrict to just matrix operations in our neural network layers. By having this flexible approach to designing tensor operations, we can compress the existing networks by such huge amounts and in fact have better performance. So we have smaller models with better accuracy and other performance metrics. And in addition, by building good GPU primitives, we can also get great speedups with it. So in that sense, you're winning in every way by using tensors. So I encourage you to go try out Tensorly and contribute to the open source community there. So that was the aspect I wanted to showcase, with Tensorly and tensors. I want to now show you a few other examples of how we are combining algorithmic research with new frameworks and good infrastructure support at NVIDIA. And one of them is NVIDIA Isaac, which is the platform for robot learning. Indeed, these are exciting times where we are envisioning robots that can be autonomous, that can interact with us, that can do all kinds of challenging tasks. And to do that, the Isaac platform, what it enables us is not only to train on real robot data, which is little to come by and expensive to collect, but also build highly realistic, physically valid simulations so that you can train in simulations to a much greater extent compared to the real world. And this is built on top of the EGX stack, which is the AI stack for the edge. And so you can directly deploy these models also onto the edge devices that run on Jetson and Xavier, for instance. And there's also the exciting 5G capability available with the aerial part of the EGX platform. So you can have good connectivity, you can have good intelligence with AI training, and you can have good edge performance. So all these are part of the ecosystem for edge devices. And the aspect where we are contributing extensively is on the development of the AI algorithms. And one example is this paper that got accepted to Coral just yesterday. And what it shows is if you just have a baseline robot model that tries to walk on surfaces it's never seen, it'll fall, right? So this banana peel is a surface with no friction. Whereas we trained a reinforcement learning-based control that not only can avoid falling off on a banana peel, but also do that in the real world robot. So here I only have a short video. The long one is available both on my website and both if you Google this, there's even articles on this. And the idea is how we can train good controllers like this in simulation and then deploy them in the real world. And the way we went about this was doing it in a hierarchical way. So the RL controller only decides how to mix the primitives. So the primitives could be like whether it's walking or trotting or just standing. So how to mix them up. So that's what reinforcement learning is used for. And so in the real robot, as long as these low-level controllers are good and they have the robustness properties because that comes from control theory, so you can now add learning and adaptivity seamlessly and do it through simulations. So that's been the exciting part. And so in summary, NVIDIA Isaac is a great platform for us to try out new reinforcement learning and other adaptive learning methods. But it also has physically valid simulations, so you can then port them to the real robots. And it's also GPU accelerated, so we can run reinforcement learning at scale, and we can build all kinds of new algorithms. So we can do lots of interesting sim to real methods through these platforms. So I want to now take some time to discuss about how an AI stack should look like and how NVIDIA is approaching this. So if you think about it, in the beginning, there was only CUDA, right? But that was great universal platform because you could program, GPUs and then deploy them on so many variety of applications. But now with AI and machine learning, right, you need higher order primitives. And that's where frameworks like PyTorch, TensorFlow, right, will be effective in enabling developers to do that. But it's not just about writing deep learning algorithms. If you think about end-to-end pipelines for machine learning, it involves data analytics, right? It could involve graph and other kinds of special structured methods. So those are aspects as well we want to worry about. And that's where Rapids is reimagining the AI workflow. So not just to focus on model training, which is what the rest of the frameworks do, but add in the data preparation visualization and accelerate it end to end on GPUs. And then through Dask, have the ability to scale it out to multi-GPU and multi-node. So as you can see, QDF is, is built on the data frames framework, but now accelerated on CUDA. And similarly for graph analytics, even classical machine learning in addition to deep learning. And so the main principle here is we avoid the CPU to GPU communications. The basic Hadoop has just not even in-memory processing, right? So each time you write it up to disk, read it, this is just impossible. In each stage, first you query, you do ETL, you do ML train, very expensive and all on CPU. Then Spark made it in memory, so it avoided the reads and writes between querying and ETL. But on the other hand, it's still on CPU. And now to bring it on GPU, you can make it efficient, but you still have to read it back into the GPU and write it back to CPU, right? So that was the traditional one. And what Rapids does is get rid of all of this. So keep everything on GPU directly from querying ETL all the way to train and then visualization. So by avoiding this CPU-GPU communication, you can get 100x or more improvement. And there's lots of real-world use cases where this has been demonstrated. XGBoost, which is very popular method, which wins probably the largest number of Kaggle competitions. The Rapids version of it has great speed-ups there. And you can also, as I said, scale it out with Dask and get performance even on multiple GPUs and multiple nodes. So you can access more resources. This is an open source project, so notebooks and examples are all available online. So check it out. There's an active community on Slack, Twitter, and other platforms. So I encourage you to go check it out. If you're running different AI workflows, this is a great way to utilize the GPU acceleration, but with minimal code changes. Literally, it can be just one line of adding Rapids, because all the scikit-learn and different frameworks, pandas, if you have those existing ones, you can seamlessly now get GPU acceleration with Rapids. And in addition to what I showed, there are many other great verticals where now NVIDIA is saying, let's have a platform with pre-trained models, with good transfer learning toolkits, with good ways to deploy the models, and make it easy for domain specialists who don't have AI background to easily start using AI. And that's where NVIDIA CLARA has been a great success story. It started with medical imaging, right? So where having annotations is expensive, so can AI assist having the annotations? Can we do good transfer learning? And can it be deployed on all kinds of devices, including the edge, such as scanners and other medical devices? This is also available. And at the recent GTC, we had many exciting announcements, including using this platform for drug discovery and having federated learning with many hospitals to do scans of lungs for COVID. So very timely and important to enable AI in the healthcare space. So this is an example of how we can take our AI knowledge, we can build good infrastructure, we can make these models efficient, and we can make them easily usable by people without any deep AI expertise. And Omniverse is another example of platform now aimed at merging graphics and deep learning, which are the two facets for NVIDIA, and putting them together now and making it very much usable by artists and other graphics designers. So the ability to use all kinds of different interfaces and tools there and get GPU speed ups is a great platform where we are using this to do AI-based speeding up of rendering and other processes in graphics. So it's an interesting question, will GAN one day take over traditional graphics, or which aspects will it take over? So there's an exciting interplay between AI and graphics that we'll see more results in the coming years. Yeah, so the other aspect is conversational AI, which involves multiple modalities. Most of conversational AI today is just language and text, right? Whereas in the real world, having that human interaction, seeing somebody's face, their body language is so important. I mean, even just doing this virtually on a screen, right? We know we already miss so many of these nonverbal cues. So it's not the same as you seeing me in real life. So there's so much there in terms of for humans to have conversations beyond just the text. And that's what Jarvis enables, this multimodality, having videos and sound and text all come together, and being able to have different kinds of, you can then have gesture recognition, you can have these chatbots, multi-speaker transcription. So all these different modules come together. Again, having a great set of pre-trained models, as well as the ability to train your own model efficiently. Yeah, so I gave you an overview of different frameworks and platforms for some of the exciting areas in AI. I started with tensor methods and how Tensorly enables this development of architectures with tensor layers that not only lead to compression, but better accuracy and other performance metrics. And we're also looking at better primitives for GPU acceleration. So we are getting gains in so many facets by going beyond matrix operations to tensors. Then I talked about rapids enabling end-to-end GPU acceleration all the way from data access preparation to visualization, and making it seamless also for existing workflows to be brought into GPUs, whether it's scikit-learn and other frameworks with almost no code change, you can get that to rapids. I also showed many other vertical platforms. For instance, for robot learning, Isaac has enabled us to show the ability to do impressive tasks on real robots, like walk on slippery surfaces that it's never seen, because we could extensively train in simulations to have this adaptive behavior, and the simulations are physically valid and are of high fidelity. And CLARA is doing the same for healthcare, enabling medical imaging, genomics, drug discovery to go forward, and especially relevant in these times of the pandemic. Thank you so much.
Thank you, Anima. Thank you so much. And I see a few questions that have come in. And one question that came early on, before you talked about Tensorly, was asking about what would be, in your opinion, the best open source libraries for working with tensors for operations and visualization using Python?
Yeah, so the answer is Tensorly.
That is a question came at 2:39.
I guess they were thinking on the right lines, so I'm glad. Yeah, so I think, there are many others, right? But most of them are focused more on the quantum domain because that's where it was popular before, getting on to the use cases in machine learning. So they don't work with the deep learning frameworks. They, don't have GPU acceleration many times. So all these are aspects that Tensorly aims to solve in one shot.
I knew the answer to that one, even though I'm not an expert in this topic. Okay, I have another question here, and it says, it's someone actually grabbed a question from Twitter and posted it on the Q&A. It reads, in the trinity of AI, should domain knowledge be added there or somewhere else in the process?
Yeah, that's a good question. For me, that comes with the algorithms facet, right? Because I broke down the algorithms in terms of data priors and task design and action design. So for me, I view it within the framework of algorithm design.
And I think this is a follow-up question from, or no, it seems it comes from a different person. Having said that generalized learning and recognition is the goal, who is leading in the field right now? And if you were to compare the current state of the art to the age of a human baby and its ability to learn and make decisions, what age are we at?
That's a good question. I guess we are not even at the age of single cells, right, in many ways. Because if you think about even single-celled organisms, including the virus that has brought humanity to its knees, I mean, they're highly intelligent and they can rapidly evolve. These are not abilities any of the current AI methods can do. So I would say, I mean, getting to humans is so far off. We should probably start with virus, bacteria, maybe C. elegans, which is the single-celled organism with I guess just what few hundred neurons. So we are not even there, right? Because the ability for them to adapt, the ability with which they interact in the environment and are robust to so many kinds of unseen scenarios. Yeah, so it's a good question. Are there good ways to simulate that and see can the current AI methods do well? So we did release one of the challenges called the Bongard Logo Challenge. This is inspired by the Bongard puzzles from the 60s. And the idea was, if you look at the shapes, they're extremely simple looking shapes, right? So you would think deep learning method would get 100% accuracy. But the catch is it's a few shot learning where there's just 6 positive and negative examples in each instance. And each instance has a different concept. For instance, how many lines are in this image or whether the shape is convex or concave, right? So many concepts like that and tens of thousands of problems to solve. And so when you give these kinds of challenges, even the best meta learning and all the sophisticated AI methods perform very poorly compared to humans. So that shows that, it doesn't have to be very challenging, rich scenes, even say in images. It could be extremely simple shapes, and even there, challenging AI methods to do concept learning and reasoning is still very primitive. They're not there yet.
I wonder if you'd like to stop sharing your screen and
that's a good
get a better sense of your hand gestures.
Okay, yeah, now it came.
There we are. Yeah, so another question here says, well, by the way, the first part of the question said, I was asking him about your opinion on who is leading in the field right now about generalized learning. And you skipped that.
On purpose, since I personally work on that, I think my opinion will be inevitably biased. So I believe, we are doing exciting work, both at NVIDIA and at Caltech, especially, talking to neuroscientists like Doris, with whom I'm closely collaborating. So, but indeed, there are many others doing very important work in this area. I mean, Josh Tannenbaum comes to mind at MIT, for instance. But I don't want to, again,
But
pick
of
and
course,
choose, right? Like there are
we
too
know
many good names. So,
we
so
know
I
that you
understand.
are one of the leaders, of course, in the
Yeah.
field, and so we are lucky to have you. And I have a couple of more questions that have come in. One person is asking, short and sweet, do you know of any interesting applications of tensors in finance?
I mean, indeed, for instance, the TENSOR-TRAIN model that I displayed, right, we used convolution because it was images, but the earlier version of it was just purely for forecasting. I mean, forecasting is the bread and butter of finance, right? So whether it's short term or long term. So that would be the most immediate use case of an existing model.
Great. And then I have a question that says, you touched on the topic of safety. For example, in self-driving cars, and ethics, for example, the black box criminal evidence judges, bias in training models. Who, in your opinion, should be leading the way in ensuring that we don't go in a completely dangerous and ethically wrong direction with ML and AI? And what efforts are there?
Yeah, I think that's a great question. And I'm always saying it should be a community-led effort. Right. I think the tech-centric view that tech can solve everything, engineers are the modern day heroes, we can answer every question is wrong. And I think that's what has led to so many blind spots. We should talk to policy experts, psychologists, anthropologists, all right, other areas too, to come up with who are the stakeholders? I mean, who is AI affecting here? What is the backup? Right. So it also requires time to think this deeply. And so the Silicon Valley culture of move fast, break things is really not suitable for AI. It worked with, scaling up internet. It worked with having consumer social platforms, right? It worked with enterprise tools. But AI is not equated to that. So I see in many companies to use that same formula. But AI is so much deeper than building a infrastructure or having like, okay, we've deployed this is done, right? We don't need any more other than just basic maintenance. It's constantly evolving. We are so far from the final answers. So I think any company that thinks of it as traditional software will not be around for long.
Yeah, I'm very glad you mentioned the community. I also, it reminded me of the Turing lecture by Ben Schneiderman at the University of Maryland. He's a pioneer in human-computer interaction, and he was proposing the idea of there's a national safety board for national transportation safety board. If there's an aviation crash, they all come in and do the studies. He was proposing a sort of safety board for algorithms, the idea of algorithmic accountability through monitoring, constant monitoring, and then also the kind of investigation after an issue had occurred. So that's a very interesting position.
Indeed, right. But the hope is we won't be doing it after some catastrophic results. And
hopefully not.
And it's also for, very hard sometimes even for others, the public to glean that it was a bad one, right? I mean, we've seen social media now attempting to destroy democracies. But so many people don't even realize that. Whereas a car crash and an airplane crash, it's so visceral that they're like, oh, there's something wrong here.
Yes, he was looking at 3 different stages now that I remember. The first stage was like the planning stage. For example, like we have in construction, if you want to make a building, you have to write your plans and you have to have those plans approved. Yes. And so to think about the possibility of kind of planning out your algorithmic product and then having it approved by a process is so far out of what we experience now. So a person from the audience agrees on the community approach. And another question about applications of tensors, this time in genomics. Do you know of any?
So we've been in the past looking at the use of tensor methods for learning good topic models. So topic models are, they're also called as admixture models in genomics. So they're a popular class to kind of look at, right, what are the underlying topics or components without having hard clustering requirements of separability. So that would be an immediate one of an existing method, but there can be so many other aspects of, not just having genomic data, but like say medical imaging and other modalities, right? So having that, you can look at what is the interaction between the modalities using tensors as another application.
It seems that tensors are everywhere. I remember studying tensors in my solid mechanics class and Einstein notation at Caltech, and it was all, old-fashioned way. And now we have computations for all that. So now I want to imagine how our physical models that we build in my world in engineering, based on PDEs and the standard discretization methods, might be re-implemented, rethought, written to take advantage of tensor algebra and tensor hardware.
Absolutely. And you're right on target there, because that's another area we're working on. And in fact, we've used graph neural networks to learn neural operators, and inspired by multipole methods, how we can like have multi-level graph networks. So you get the benefits of these traditional methods, but with the speed up and better efficiency from deep learning. So that to me is just the beginning, right? Like how we can reimagine these scientific applications by looking at the inspiration and again some domain specific constraints from that domain, but adding now the flexibility of data driven methods. And so a lot of tensor algebra is natural to those domains. So I see a lot of excitement moving forward.
There's 1 more minute left in our allotted time, and I don't see new questions. So I'm going to ask one more question that I had thought about for you. I know that you have a background in engineering. Your first degree is in engineering in India. I don't know how the engineering, regular courses are in India, but here, I'm an engineer as well. Here, the linear algebra class in an engineering classical education is, for some reason, historical reason that I'd like to find out, is the first proof-based class. So engineers don't get the feeling of the applications and all of the wonderful usefulness of linear algebra, and instead are proving theorems for the whole semester and then want to forget and never go back. So how would you redesign the linear algebra class for engineering?
Yeah, that's a great question. I think linear algebra is now at the foundation of machine learning, right? And so I think having that theoretical foundation is good, because you need to kind of understand what rank means, not just think of a matrix as rows and columns, right? And that's the main difference. Like people who have done theory of linear algebra well know that it's an operator. And I think that's a good point of view, because how to design good low rank representations and have good manipulations, and treating that as an end-to-end view rather than, okay, it's just an array, makes a difference. But I think integrating that course with now all these programmable tools, whether it's Tensorly or even just for basic linear algebra, right, we have GPU acceleration with QPy. So why not just have some quick exercises? For instance, in my class at Caltech, in Foundations of Machine Learning, we cover a whole range of topics, and Tensors is one small portion, but I asked them to write some simple programs in Tensorly, try out some deep learning models. So I think that kind of, right, then there's a connection to practice. So I think that's important. And
I'm so glad you said that.
Yeah. And speaking of engineering, I did electrical engineering, and I'm so glad I did that because having signal processing background, thinking of, there's this Fourier representation of the signal, right? And going from there to a neural network to represent any signal, it's just so natural to me. In fact, that's how the proof works, right? You first look at the Fourier decomposition, and then you replace each of the sinusoids with rectified linear or other units, and you can make the basis adaptive. So I think that was great foundation for me. And now, with the data science major and minor at Caltech and even at other places, it's this more comprehensive view combining CS, EE, other aspects of math and engineering coming together. I think that's a much better foundation for working in AI and machine learning.
Yeah, that sounds wonderful, and I'm so glad to hear your answer. Okay, everybody, I see we've just gone a little bit past the time, so I'm going to stop the recording. And thank you very, very much, Anima, for accepting our invitation to keynote at JupyterCon 2020. We really appreciate it. Thank you.
Thank you so much, Lorena. You did so much work in the background for this, and it's a great community, and I hope more usage of Jupyter and more contributions to Project Jupyter. So I wish you all the best. Thank you.
Thank you.